3 facts about integer divisibility. The first fact that we shall look at is that we can chain divisibility. If a, b, and c are integers, and if a divides b and b divides c, then a divides c. So, for example, 4 divides 24, since 24 equals 6 times 4, and 24 divides 144, since 144 equals 6 times 24. Also, 4 divides 144, since 144 equals 36 times 4. So 4 divides 24, 24 divides 144, and 4 divides 144. So we have this pattern of chaining, 4 to 24, 24 to 144, 4 to 144. And this pattern always holds. And the following factorization shows why this is the case. 144 is 6 times 24. 24 is 6 times 4, and we can regroup the 6 times 6 to produce 36 times 4. So we can multiply 4 by some integer, in this case 36, to produce 144, which is the same as saying 4 divides 144. Similarly, we have that 3 divides 27, 27 divides 351, and 3 divides 351. We see that 351 is 13 times 27, and we can factorize 27 into 9 times 3, so 3 must divide 351. Since 117 times 3 is 351, with the 117 coming from 13 times 9. And we now prove this result. Suppose that a, b, and c are integers in the set Z, then if a divides b and b divides c, then a divides c. And we can describe that by saying that divisibility is transitive. It has this chaining property. And the proof of this is quite straightforward. Since a divides b, then b equals k times a for some integer k, for some k in z, i.e. we can make b by multiplying a by some integer k. Similarly, since b divides c, c equals lb for some l in z, for some integral l. And now we use the fact that we can factorize b. C equals lb, but b equals ka. So c becomes L times Ka, and we can regroup the multiplications to give L times K times A, which we write as M times A. And now we're done, because M equals L times K, and since the product of two integers is an integer, we have that A times some integer M equals C, so A divides C as required. The second fact that we shall look at is this. If A divides B and C divides D, then the product of A and C, AC, divides the product of B and D, BD. And so we have an example. 7 divides 49, since 49 equals 7 times 7. 13 divides 52, since 52 equals 4 times 13. And 7 times 13 divides 49 times 52. Or, to put it another way, 91, which is 7 times 13, divides 2,548. And that is the case since 2,548 equals 28 times 91. And for the example above, we have 49 is 7 times 7, 52 is 4 times 13. Regrouping the multiplications, we can take 7 times 4, put it at the front, and that leaves 49 times 52 equals 7 times 4 times 7 times 13. But 7 times 4 is an integer, so we can create 49 times 52 by multiplying 7 times 13 by an integer, so 7 times 13 divides 49 times 52. And we will now prove that this pattern always holds. So the fact that we want to prove is if A, B, C, and D are integers in the set Z, and A divides B and C divides D, then AC divides BD. And to start, we use the definition of divisibility. Since A divides B, B equals K times A for some integral K. And since C divides D, D equals L times C for some integral L. And now everything is quite straightforward. We are interested in B times D. B is Ka, D is Lc, so BD is Ka times Lc, which we can regroup as KL times AC, which is M times AC, where M, which equals KL, is an integer, as it is the product of two integers. So since we can multiply AC by an integer to produce BD, then AC divides BD as required. The third fact about divisibility concerns so-called linear combinations. So 7 divides 21 and 7 divides 77, and it is the case that 7 also divides 21p plus 77q regardless of which integers we choose for p and q. This is true for all pq in Z. And this particular way of combining 21 and 77, the 21p plus 77q, is called a linear combination. And it's straightforward to see that 7 divides that linear combination. 21p is 3p times 7. 77q is 11q times 7. We factor out the 7s to the end to leave behind 3p plus 7q, and 3p plus 7q is an integer. Since the product of two integers is an integer, here we have the product of two integers, here we have the product of two integers, and the sum of two integers is an integer. Here we have the sum of two integers. And of course, this doesn't just work for the numbers 7, 21, and 77. This pattern always holds. If A divides B and A divides C, then A divides any linear combination of B and C, i.e. it divides PB plus QC for all integral P and Q. And there are two important special cases. For the first, take P equal to 1, Q equal to 1, and then if A divides B and A divides C, then A divides B plus C. For the second, take P equal to 1, Q equal to minus 1, and then if A divides B and A divides C, then A divides B minus C. And so we prove this fact. Suppose A divides B and A divides C, where A, B, and C are integers in Z, then for all P and Q in Z, A divides PB plus QC. And we could say that this is telling us that linear combinations maintain divisibility, where this construction, PB plus QC, is a linear combination of B and C. And so for the proof, we start by expressing these facts, A divides B, A divides C, using the definition of divisibility. So A divides B implies that B equals K times A for some integral K, and A divides C implies that C equals LA for some integral L. And now we proceed much as we did with the 7, 21, 77 example. PB plus QC equals P times KA, since B equals KA, plus Q times LA, since C equals LA. And now we just factorize out the A to the end to leave behind PK plus QL times A. And now we note that pk plus ql is an integer, so we can create pb plus qc by multiplying a by an integer. Therefore, by definition, a divides pb plus qc as required.